Okay, so let's dive in. Imagine this. By the year 2100, our planet's coral reefs, these incredibly complex, vital ecosystems, are predicted to be, well, gone. Not just bleached, but fundamentally replaced.
Replaced by, of all things, simple fleshy algae. It's a really dramatic forecast, and you hear it and think, okay, that's probably from a computer model, right?
Exactly, some abstract simulation. But the source material for our deep dive today is different. This is based on an international study published in Communications Biology that found a way to observe the future directly.
They found nature's own laboratory. This whole thing was led by the Australian Institute of Marine Science, AIMS, and they found a shortcut.
A shortcut to the future, I love that. They found it near these shallow submarine volcanoes in Papua New Guinea, PNG for short.
Yeah, and these sites are just naturally venting almost pure carbon dioxide right into the ocean. The senior author, Dr. Katharina Fabricius, she called it a time machine.
A time machine. It's the perfect description. It lets researchers see what reefs look like when they've been living for generations under the exact conditions we're projecting for the end of the century.
It's invaluable, really, because you're not just looking at one organism in a tank, you're seeing how the entire community, the whole interconnected web, responds.
Okay, so before we get to PNG and what they actually saw in that time machine, we should probably do a quick refresher on the threat itself. Ocean acidification.
Right.
We all know the ocean absorbs a massive amount of the CO2 we pump out, something like 30 or 40% since the Industrial Revolution. But maybe break it down for us. Why is that so bad for coral specifically?
Well, it really just comes down to basic chemistry. When CO2 dissolves in seawater, it forms carbonic acid. It's a simple reaction.
And that acid lowers the ocean's pH. So the water is literally becoming more acidic.
Exactly. And that's the core of the problem. That rising acidity is corrosive to anything built out of calcium carbonate. That's shells, but most importantly, that's the limestone skeleton of the corals themselves.
So the very framework of the reef is, it's slowly dissolving.
It's being eroded, yeah. Now, to give you some numbers, oceans are naturally a little bit alkaline. The pH is usually around 8.1, maybe 8.2.
But our sources say that acidity has already gone up by 30%.
Already, which is a huge change. And the projection for 2100, if we stay on a high emissions path, is that the pH will drop even further, down to around 7.8.
And that might not sound like a big number, that drop from 8.1 to 7.8, but the pH scale is logarithmic.
Right, so that small-sounding dip is actually a massive environmental hurdle for these organisms. It makes building their skeletons so much harder.
And the team looked at an even worse case, didn't they? If atmospheric CO2 hit something like 1,000 parts per million.
They did. At that point, pH drops below 7.7, and the study is pretty clear. Reef building as a process basically stops. Coral reefs as we know them, these big, complex structures, they just cease to exist.
You might get a few tough, bouldering corals left, but the ecosystem, the thing that supports all that life, is gone.
Gone. And understanding that chemistry, that slow erosion, is really the key to understanding what they saw in Papua New Guinea.
Okay, so let's go there. How did they even find this place? It's an amazing story.
It really is. It started way back in the year 2000. Dr. Fabricius was just doing routine species surveys in Milne Bay, super remote place about 500 kilometers east of Port Moresby.
And while she was diving, she just kept noticing these streams of bubbles coming up from the reef.
Yeah, just streams of gas coming right out of the seafloor. At the time, ocean acidification wasn't the huge issue it is today, so it was just an oddity.
Curiosity.
Exactly. It wasn't until almost a decade later, 2009, when the science on acidification just exploded, that she remembered those bubbles.
And she had the gas tested.
She did. And the result, pretty much pure CO2. That's when she knew she'd found her natural laboratory.
And you just have to think about the logistics of this. This isn't a place you can just drive to. The sources mention a flight to PNG, then another flight, then a 6-hour boat ride.
Just to get in the water.
Just to get in the water. That level of effort really tells you how important they knew this site was.
It does. Because their goal wasn't just a quick look. They wanted to see how these ecosystems adapt over generations. How do they acclimatize? You can't get that from a lab experiment.
No, that's the key. A tank can show you immediate stress, but this place shows you what survival looks like after decades of that stress.
And we should also mention the local people there in Milne Bay. The study makes a point of saying how welcoming they were and that this kind of long-term research just wouldn't have been possible without their support.
Absolutely, a crucial human element to the science.
No.
Okay, so they have their site. They set up 37 different study areas along a 500-meter line, a gradient, moving from normal pH water closer and closer to these CO2 seeps.
So it's literally like walking into the future. The further you go along that line, the lower the pH gets until you're at the levels predicted for 2100.
And what did that walk into the future reveal?
Well, the first big surprise, the thing Dr. Fabricius noted, was that there was no sudden collapse.
No tipping point. We always hear about tipping points in climate change.
Right. We expect this one moment where everything just breaks. But that's not what they saw. It was progressive, gradual, relentless.
A war of attrition, not a sudden catastrophe.
That's a great way to put it. It's a slow, steady replacement of species.
Okay, so what was being replaced and what was doing the replacing?
As you move along the gradient towards the low pH water, the first things to struggle are the calcifying organisms, so the branching corals and also these calciferous algae that kind of act like cement for the reef.
They can't build their structures as easily. They get weaker.
Exactly. They get weaker, they grow slower, and they just can't compete anymore. And something else moves in to fill that space.
The fleshy algae.
Fleshy algae. They become completely dominant. They don't need to build a calcium carbonate skeleton, so they actually do pretty well in the higher CO2 water, and they just smother everything else.
So the signature of severe acidification isn't a white, bleached reef. It's a reef that's been covered by a thick carpet of, what, slimy green algae?
That's it. You go from this complex, three-dimensional city to a two-dimensional, low-lying mat of plant life. The structural complexity just vanishes.
And Dr. Fabricius said this is basically the clearest prediction we have for what places like the Great Barrier Reef will look like.
It is. This is what the future looks like. So if this is a slow, progressive takeover, what does that mean for a reef's ability to bounce back from other things, like a cyclone or a bleaching event from heat?
Right, because acidification isn't happening in a vacuum.
Not at all. And this is where it gets really alarming. The first author on the study, Dr. Sam Noonan, he pointed to one very specific, very bad sign.
Which was?
They found far, far fewer baby corals in the high CO2 areas.
So recruitment is failing?
Yeah.
The next generation just isn't showing up.
Exactly. Recruitment is the lifeblood. If you don't have new coral larvae settling and growing, the reef can't repair itself. It can't regenerate after a disturbance. It becomes a system that can only ever degrade.
And that inability to recover, that connects directly back to us, doesn't it? I mean, why should someone listening to this in, the middle of a continent care about baby corals in the Pacific?
Because of fish. It's always about the fish. That complex 3D structure of a healthy reef. It's a nursery. It's full of caves and crevices where juvenile fish can hide from predators and find food.
So many commercially important fish start their lives on a reef.
So many. So when you replace that complex city with a flat carpet of algae, you've erased the nursery.
No nursery means fewer adult fish.
Which means a potential disaster for the millions, even billions of people in coastal communities who depend on those fish for food, for their livelihoods, for their culture. It's a massive cascading effect.
And this research is not a model anymore. It provides the real-world proof of that entire chain reaction.
That's why it's so important. Dr. Fabricius said that acidification is this massive global problem that's kind of been underreported compared to warming. This study gives us that real field data showing how a whole community changes.
So to recap, the time machine in PNG shows us that the future for coral reefs isn't necessarily a sudden collapse, but a gradual, profound shift.
A shift away from coral and towards algae, which cripples the reef's ability to recover from anything else we throw at it.
And it directly threatens the fish stocks we all rely on.
That's the essential takeaway. But let's leave you with one final thought based on that subtle but really important distinction the study found.
Okay.
There was no sudden tipping point. It was a gradual but profound shift.
And a tipping point is dramatic. It's a headline. It's a clear crisis moment that can, hopefully prompt action.
Exactly. But if the collapse is slow, if it's a progressive replacement that happens over decades, not in a single shocking event, does that make it harder for us to see?
Does the lack of a single dramatic moment make it easier for people, for policymakers, to ignore the severity of the crisis until it's truly too late? That's a really interesting and, frankly, a scary question.
It is. A slow motion crisis might be the hardest one to fight. Something to think about until our next deep dive.